Right, we're going to continue our insane streak of theorems because we're unstoppable and we're amazing. Now, a parameterized surface is locally a map. Part 1 theorem. I have decided to split this theorem into 2 bits to be more digestible, and the name is very suggestive for what it says. So what it does. So let's delve into our first geometry theorem. So what are our assumptions? Well, let phi be a map mapping some subset U of the k-dimensional real space into the m-dimensional real space, be a parameterized case surface. Then, to each element U0 from U, there exists a neighbourhood U0 such that it is a subset of U and such that U0 is in capital U0 and second and phi is invertible on U0, or simply is invertible thereon. We shall actually prove something much stronger. We should prove that it is a diffeomorphism on U0 using the local diffeomorphism theorem, but I'm getting ahead of myself. My point is we're going to prove actually a stronger result. Now, how do we go on about proving this? Well, I have spoiled it just a little bit. So what do we do? Well, we know that the rank of the vector derivative of phi of U0 is k. We know this by the definition of a parameterized k surface, so I'll simply say by assumption. But it follows from the definition of a parameterized k surface. This means then that there exists, so then by the Cauchy-Binet formula, there exists a square k by k sub matrix of d phi of U such that, this is important, such that it is non-singular. Now, we can, without any loss of generality, assume that these are the first k columns and rows which make up the non-singular k by k submatrix. If it were not so, we would simply change the notation, permutate the rows or columns or whatever to obtain such a matrix. So we don't have to bother with permutations. Let's just assume that it is the first k rows and k columns form the submatrix. So without any loss of generality. Let the matrix or the submatrix del phi by del uj of u0, where ij range through 1 to k, or like this, to k being non-singular. Again, if it were not so, we would simply change up the rows. Now, then the map G, which maps an ordered k-tuple onto another k-tuple, has a non-singular vector derivative at u0. Well, now, using the, and I shall comment on this further, using the local diffeomorphism theorem, we obtain that G is a diffeomorphism, at least on the limited local interval, on capital U0. Well, why can we even use the local diffeomorphism theorem? Well, there are two main prerequisites which we both meet. One, it must hold that the map in question is has continuous first derivatives, partial derivatives, with respect to all the variables. This is the case because we know that phi is smooth. It is right there in the requirements, in the assumptions. By assumptions, phi is smooth. And as such, all of the partial derivatives of G will be continuous. And as such, we have continuous first derivatives. So that's the first requirement met. The second requirement is that the Jacobian of the map is non-singular, which we have explicitly discovered. So all the requirements are met, and using the local diffeomorphism theorem, we arrive that G is a diffeomorphism on U0. Well, this is precisely what we wanted. Because since G is a diffeomorphism when restricted to U0, then in particular it is invertible. So, thus, particularly, or in particular, thus in particular, G is invertible. And this concludes the first part of the parameterized surface is locally a map theorem.